All right, so welcome back to part 2 of the lecture. I learned something useful, namely that this camera does not like lectures that are longer than about 46 minutes. But hey, live and learn. This is an exciting learning time for all of us. So I'm going to resume this about where the other lecture cut off. I'm going to do a bit of an overlap, but feel free to just skip ahead. So we had just talked about rest energies in terms of MeV. So a neutron was 9.39.6 MeV, which is equal to mc squared. The proton, 938.3 MeV. The electron, 0.511 MeV is equal to mc squared. So we can use this relationship to get mass in terms of energy. So using E equals mc squared, we see that m is equal to E over c squared. Okay. So we can express mass in terms of rest energy. So using that, then the neutron, we have 939.6 MeV per c squared. The proton, 938.3 MeV per c squared, and the electron, 0.511 MeV per c squared. Okay, so when we're looking at the energy principle with respect to particle interactions, this is the type of scale here and here that we're much more likely to use to express for both mass and rest energy. These are just not super tiny units. And remember, at the end of the day, physics is all about, I want to make my life as easy as possible while solving really cool equations about the universe. Okay, so we're going to use this understanding now to explore neutron decay. So using our brand new unit, let's look at neutron decay, because it's also really fun to say. Okay, so in our neutron decay, we have a neutrino. So in neutron decay, one product is the neutrino, which is nearly massless. So we'll treat it as though all energy is in the form of kinetic energy. So almost like you would treat a photon, except for with a photon that is true. All energy is kinetic energy. But if you don't believe me, feel free to look up the masses of neutrinos and antineutrinos, and you'll see that this estimation actually works pretty well. So I always encourage you to prove these concepts to yourself. Actually, the decay product for in the neutron decay is actually an antineutrino. So same mass, opposite charge. So our neutron is going to go into a proton plus an electron plus an antineutrino. That is the symbol for an antineutrino. And we're going to express energy in terms of MeV. So to set this up, once again, we need our system. This is going to be all particles before and after. So now, even though we're going to have an identity change, it's perfectly fine to say, whatever we start with, even if it's different than what we end with, this is still the same system. So the surroundings, neutron decay happens pretty fast, so there's really nothing that's going to impede that. There's no reaction time. It's too fast. So remember, look at the assumptions we're making in lecture. This will help you as you're making assumptions in your homework and exam and quiz problems. So initial state, we've got the neutron at rest. And the final state, we have the proton, the electron, and antineutrino. And they're far apart. So what we mean by far apart is they're no longer interacting. So they're just chilling, doing what particles do. Okay, so we're going to be using the energy principle for this. We have their masses, or we can look up their masses. For the neutrino, we're going to go after it using basically we're going to use the energy principle to learn about the neutrino. And the question we want to answer is how much kinetic energy do the decay products share? So you're looking for energy. That pretty much indicates that we're going to be using the energy principle. Okay, so moving along, if we're using the energy principle, so I'll be abbreviating this often EP. This is just an abbreviation for my class, just to make things easier. So energy final is equal to energy initial plus any work from the surroundings. All right, let's flesh this out. So we have the mass of the proton times c squared, which is a constant, plus the kinetic energy of the proton, plus the mass of the electron. So we've made no assumptions about whether or not those particles are moving or not. All we know is that energy is conserved. So mass of the electron times c squared plus the kinetic energy plus the kinetic energy of the neutrino, and it is massless enough that it's not useful to include. So we have the mass of the neutron times c squared plus the kinetic energy of the neutron initial plus work from the surroundings. Okay, so where are my zeros at? There's a couple useful things. So we were told the neutron started at rest. Therefore, it has zero kinetic energy at the beginning. We were told there was nothing interesting in the surroundings. So work is also zero. Are there any other zeros? Let's see. This is different from this, and this is different than this. And okay, well, that's all the zeros we've got. All right. So we've made it a little bit easier. Now we can start plugging in knowns. So plug in knowns. Kind of makes sense to do that now. So we know mc squared for a proton, so that's just 938.3, let's write that correctly. 938.3 MeV plus the kinetic energy of the proton, which is unknown, 0.511 MeV plus the kinetic energy of the electron plus the kinetic energy of the neutrino is equal to 939.6 MeV, our only non-zero factor from the right side of the equation. So moving along, let's go ahead and pull out those kinetic energies. So kinetic energy proton plus kinetic energy electron plus kinetic energy antineutrino plus 938.8 MeV. So all I've done is I've taken my nice little integers, or they're not really integers, my nice numbers, and I've added them together. And this is equal to 939.6 MeV. All right, so this is what we're after. So then we can just subtract from both sides. And we get that the sum of the kinetic energies of the decay products is equal to 0.8 MeV. All right, and we've also learned something interesting. So a proton cannot decay into a neutron because that would be a violation of the energy principle. A neutron has far more energy than is available to the proton. So energy is always conserved. So And the energy principle has been responsible for the discovery of several new particles, including the neutrino. So we've known about neutron decay for a while, and there was some missing energy when we would do these measurements, and that was this mysterious neutrino particle, or the little neutral particle, as Fermi called it. So proton decaying into neutron violates energy principle. Not allowed. We don't break physics in this classroom. Even though we're online, we still don't break physics. Okay, so the last part of 6.5 that is important to discuss is the intelligent plug and chug. So we've already been doing some plugging and chugging. That basically means that, you have your formula, you put in your knowns, and you chug along and get an answer. But there is actually a method to doing this in a way where you're most likely to get the right answer. And this is invaluable to taking tests and quizzes and, more importantly, standardized tests. Well, for some of you, more importantly, standardized tests. So here are the steps for setting up a problem. I'm going to look for these steps when you set up your problem. So you want to specify system and surroundings. Who is doing the work and who is being worked on? Very important. You need to specify initial and final state. There are grave implications about what your initial and final states are. You need to write out a detailed, no-holds-bar energy principle for your system. So all the bells and whistles, and then you want to think about what do you not need. Then you're going to want to find your zeros. I mean, anything you can make go away makes it easier. Then you want to use information given to evaluate easy terms. And of course, the game you're hoping to play is that if I solve for what I think is easy, then maybe what I think is hard becomes easy. Then you solve for unknown. And remember, sometimes our unknowns hide. For example, if your unknown is velocity, it might be hidden in kinetic energy. Might be hidden in the gamma factor, etc. So just remember, you may have more information than you realize. Then last, you just want to double check. Do your signs make sense? Conceptually, does this make sense? I mean, common sense still holds in physics. Every once in a while, we have things like quantum that defy common sense. Positive, negative work, is that consistent with speeding up and slowing down? It's just a way to okay, well, this is what I would expect, or this is not what I would expect. And remember, it's just a check you can do, and if you do a concept check and realize something's gone wrong, you might be able to find it, or you can at least write me a note saying, something has gone wrong and I know something has gone wrong. I mean, that is always more assuring to me than something has gone wrong and I'm ignoring it. By the way, you've been using this for the momentum principle as well, but now you have it explicitly stated. And have been. So your book goes into more detail on intelligent plug and chug, but these steps really are the basis of it. If you do these steps in any physics problem, in a classical mechanics class, even if something goes wrong, it's probably going to be a calculation error, not a conceptual error. So these are just good things to internalize. Also, you are allowed to put them on your formula sheet. Okay. So the last thing I have to say, just 6.6 has a little energy proof, which I'm not going to do. So it is optional for 111 and on your own for 211. It's really well worth your time. So even for those of you in 111, I would highly recommend taking the time to just review where the energy principle comes from and understanding that. So that wraps up Monday's lecture. So the lecture that will be uploaded for Tuesday will start at section 6.7. So please email me any questions, schedule a Zoom meeting, anything you need so that I can help you get what you need out of this class.